All right, that seems like it's focusing enough that we can do this. So this is an attempt to look at the geometric and some of the numerical patterns. That kind of gives us a better sense of the chain rule. So we'll have at it. And we're going to look at a little implicit differentiation and explicit differentiation. Let's see if I get this a little closer. All right, so what are we starting with? Okay, a little geometry. All right, so we've got going to let x and y take on a value of 3, some easy numbers to work with. We're going to look at x squared y cubed equals 243. All right, so that's a product. A product can always be shown as a rectangular relationship. And so we've got x squared for height, y cubed for width. And we're going to look at how that area changes when we change the x and the y by 0.001. All right, so squaring 3.001 we know gets us 9.006 with some change. But we're not looking at that limit situation right now. We're just going to take the approximation of the geometric situation. And so we can see that we've changed by 0.006. Obviously, I got to get some distance here so that you can see the real layering relationship is like putting a piece of thread on the perimeter there. So 2 times 3, 6 times 0.001 gets us that 0.006 change. So that's going to be our change in the height of that rectangle. And this is held constant, 27. So there's your 2x y cubed dx geometric change. All right, so maybe I should put that somewhere. So we have, well, I did it over here. In a second, we'll look at it over here with the numbers. And this one is 3 squared is 9. That's going to be held constant. And if you look at, did I erase the y's? Oh, the y's are over here. So 3.001 cubed gets us 27.027, another 6 decimal places in change. There's a nice pattern there as well. Same, a little different pattern from the quadratic, but definitely a recognizable pattern there. So that gives us a width of 0.027, even though this is only changing by 0.001, 0.027 times 9. So that's, I guess we'll look at the implicit differentiation here and plug in those numbers and see what we get. Okay, so x squared times y cubed equals 243. 243 is not changing. Our change on the left side was 0.243 and 0.162. The 0.243, I think is over here, 243, and the 1.162 going on memory here is that one. All right, so implicit differentiation, 2xy cubed. I probably should put x squared y cubed closer to this. Okay, so no change here. 2x dx times y cubed is exactly what happened in that rectangle. And x squared, going back to the original here, x squared y cubed, 3y squared dy. It's exactly what happened in the layering process over here. And so if we actually plug in the numbers, 3 for x and 3 for y, we get 0.162 dx divided by dx. This cancels out. 0.243 dy divided by dx gets us our y prime. And setting it to 0 means I can bring the negative 0.162 over and divide by 0.243. And that's a negative 2 to 3 ratio. And I think we looked at, I think I uploaded a numerical look at implicit differentiation. So this is really about that as well. And we've got this kind of proportionality going on over here. It's not Pythagorean relationship, but it's akin to it. See, so let's look at it explicitly now. All right, and let's look where the numbers go. Let me shut the door here so I'm not bothering people down the hall. All right, so if we solve for y, we've got to divide by x squared. We've got to take the cube root, brings us here. Cube root of 243 is 3 times the cube root of 9, right? You can divide this by 27. 27 times 9 gets us that. And we can take the cube root and look at it from a power rule standpoint. I think probably the best, x to the minus 2/3. And I think we've captured this correctly algebraically. So we're going to do power rule minus 2/3 times 3 times the cube root of 9, and then we're going to drop this down 1, 3 to the negative 5/3. All right, so it's best to rewrite this now as 3 to the 2/3, and we got 3 to the minus 5/3, which gives us 3 to the negative 3/3, which is 1/3, right? Which is -1. 3 to the negative 1 is 1/3. I don't think, oh God, I'm off camera here. Okay, I'm just playing around a little bit. Can we see all of these? Yeah, I guess so. Yeah, so one more time. Cube root of 9 is 3 to the 2/3, right? 9 is 3 squared. Should be able to follow this now. We've done enough power rule. So I'm writing that exponentially because it's easier to put these together. That's 3 to the negative 1. We'll do that over here. 3 to the negative 1, which is 1/3. And 1/3 times -2 is negative 2/3. My, oh my. We got the same answer, whether we did it implicitly or explicitly. That's nice to see the numbers work. It's nice to attach it to geometry, right? And now what are the implications? Well, the implications are far-reaching. We're going to take some liberty with Descartes' coordinate system. And we could just, well, I go back to the original here. Let's go back here. All right. And what I basically did, taking a little liberty, I don't think Renee's going to mind, really creating a new axis. Okay, this is the x squared axis. It's the x squared axis, and it has a lot to do with how that width is changing. And this is the y cubed axis over here, the y cubed axis, and that has an awful lot to do with how the widths are changing. All right, so let's go over here and look at another problem that we've been working on. And let's see if I get some lights on. We shall try. Come on. There we go. Yep. So let's see if we can capture this on the screen. Yeah, good enough. So we've been looking at this relationship now for a month. I try to make some sense out of it. All right. And what we're really looking at is two axes. One, the 2x axis and the x squared axis. So we're looking at geometric change. And remember, what we're looking at is addition of area under a curve. Let's call this the curve. All right. And at what rate is it changing? If, let's say, we had an x value of 3 and we went to 3.001. Well, I probably should have different colors here, but on the 2x axis, we can see that x actually isn't 3, it's 6. And we're not at 3.0, we're doubling that, so we're at 6.002, which is giving us a 2 times, remember the change in x is 0.001. So it's 2 times that change in the x values. That's what's happening. And so this area that's accumulating is being, remember, we have a big f of b, fundamental theorem, right, minus big f of a. And so we are looking at the takeaway in this case. If this had been a negative 2x axis, we'd actually be building area on both sides of this curve. Okay, but what do we have here? Well, we have a height, and what is the height? Well, it's double the x, right? It's 2 times 3 is 6. It's f of 2x. And what is the width? The width is changing by 2 dx. Well, if I leave dx here alone, then I can put the 2 in front of this, and I can say that, oh, this layer is, we are losing a 2 f of 2x rate. We're losing it at that rate, right here. On the other side, we got the x squared axis. So, we look at 9, and I'm sorry, I'm still letting x equal 3 here. Still letting x equal 3. 3 squared is 9, but if we square it, we know we've done it enough, 9.006. Well, that actually is 2x dx. That's 2x dx. And I am evaluating, remember, this is way to the right. I'm getting a layer here. And I'm adding at this rate, 2x dx times this. So we have f of x squared times 2x for width. And that's the rate at which we're adding area on the right. All right, so let's cut to the chase. What's the shortcut? The shortcut is to take the derivative of the upper limit here, which is 2x, drop it in, and we get f of x squared minus derivative of 2x is 2. Remember, we saw it. From 6 to 6.002, we change by 0.002, not by 0.001. It's twice that change. So that comes into play. And we have to evaluate the height of our rectangles, and that is coming from evaluating the function at 2x. Okay, so hopefully, not the greatest pictures in the world, but more to chomp on, more to think about as we go through the next month and a half of study. So that gives us an opportunity to dive into these things a little more deeply. And hopefully, if you got your critical thinking cap on, you can mull this over a few times. Yeah, I would definitely. And if you really want to dive into it, then you jump into the video on the YouTube channel there. What was it called? The chain rule through the lens of integration. Okay, because I think that's where you see the chain. I know folks are trying to do it from the other side, differentiation, but I think this is where you can really see it. And that's what we want to be able to do. We want to be able to have pictures in our head as to what's going on. So hopefully you got a little picture of some geometric change at the start of the video, and hopefully you can see how we can extend that understanding into new domain. Boldly go where no area has gone before.